Like, well, it seems really divided three now.
Okay, we're starting.
I still forgot why. Almost no.
Did you play a field too? Or your PO?
So most of what I want to talk about today is conceptual, but let's start off with an example. Using the limit definition again to find a derivative and then using that. So a problem like this is pretty much, it's guaranteed to come on the next test. There's going to be a problem that's pretty much worded exactly like this. It's just that the function might be different. So we're still in 2.3, 2.4. And so here's an example. In this case, it's 3 minus 1 over x. And then b, so it would be a two-part question. Hence, the equation of the tangent line. Two factor x at the point where x equals 1. Now, by the time the next test rolls around, we will be able to compute derivatives without actually going through the limit definition. But if a question specifically says, use the limit definition, I expect you to use the limit definition. So let's actually do part A. What is the limit definition? F prime of x is given by
Limit.
X plus h minus x. Function.
f of x plus h minus f of x over h. So let's actually apply that to this function. So, and you keep writing the limit until you actually plug in the numbers. So let's actually write that in. So this guy, we're just going to replace all x's with x plus h. So that'll leave us with 3 minus 1 over x plus h. And that's our f of x plus h, minus parentheses, put the original function, f of x, over h. Now right here, 3 with 3, and I would have the limit h equal to 0 minus 1 over x plus h plus 1 over x over h. Want to simplify that? Realize that's a complex fraction, so the best way to simplify that is to multiply top and bottom by the LCD. This guy's going to distribute. So that's going to leave us with minus x plus h for h x plus h. Minus x plus x goes away, so I'll just have h over hx times x plus h. H is now cancelled. And so we will have the limit as h approaches 0 of 1 over x times x plus h. And at this point, we can plug in h without dividing by 0. So I'll just plug in h equals 0. that's 1 over x squared. They specifically asked the point where x equals 1. So this means that f prime evaluated at 1, because f prime is a function just like the other one. And I would just plug in 1. And so that would be the answer. So whenever it says use the limit definition to find a derivative, I do expect you to go through this formula. It will take you working through the algebra of simplifying the difference quotient, and then ultimately you want to plug in h equals 0, because that's how we take the limit. And the resulting function will be the derivative. This is the derivative that, remember, it will give you the slope or the rate of change of a function at a certain point. A fact we will be taking advantage of pretty soon. But for now, we will use it to find the equation of the tangent. So now if we go to B. So we remember that a tangent line is just a straight line, right? So it's the y equals mx plus b guy, or y minus y1 equals mx minus x1. So what do we need for the line? Well, we need the m value. The slope, what is the slope here?
1.
The slope is 1. That comes from part A. Right, so in part A, we went through, we found the derivative, we plugged in x equals 1. That guy you can interpret as the slope of the tangent line. Right, that's one interpretation you can put on that number. So our slope here is 1, and then what do we need? We need a point. Right? So to find the equation of a line, we need the slope and the point. We already know the x value. So we need the y value. How do we find the y value? Huh?
Plug into the original.
Plug into the original. Right? And this is something I'm going to talk about today, when to use which functions and what they mean. Hopefully we can get to a nice level of that. So I'll plug into the original function. And so this would be 3 minus 1 over 1, so that gives me 2. And so that means that x1, y1 equals 1, 2 is a point on the line. And now I have the slope and the point, I can find the equation of the line. So here I use y minus y1 equals mx minus x1. So this means y minus 2 is equal to m x minus 1. And I never asked for the line in a specific form. I never really said use the slope-intercept form. So this would be fine as an answer. You could go further and just solve for y, so your y would be x. It would end up being x plus 1. But it's not necessary unless I specifically ask for it. But yeah, that's a very typical question, and it's a very standard question to ask Calc 1 students, so there'll definitely be a question like that. Like one part of a question will be that question. Right, it says, use the limit definition to find the derivative of this function at this point. We'll do that, and then I'll say, hence, find the equation of the tangent line at this point. So a very standard type question there. Very brute and elementary, because for functions like this, we wouldn't normally use limit definition, but you're always asked to use it. After all, pretty much the only people who use the limit definition are math people, because we start to work with crazy functions that we don't know how to deal with, and we just have to go back to the definition to figure things out. But the function we'll be dealing with here, I will be teaching you shortcuts eventually for finding limits, for finding derivatives. You won't actually have to do the limit definition, but if it's asked specifically, you need to do it that way. And I'll usually put something like no credit given for any other method or something like that. here's one thing that we're also going to use a lot that I want to talk about. It's called the second derivative. The second derivative. So here's the idea. There are times we can take derivatives of derivatives. In this class, you'll always be able to do that. There are some exotic functions where once you take a derivative, the answer you get, you actually can't differentiate it. But we're not really going to see something like that, but just know that there are cases like that. But there are times when we can just keep taking derivatives. So I take the derivative of a function, and I get a new function, and I can take the derivative again. And I get a new function, I can take the derivative again. And these functions are nice. There are uses for these repeated derivatives. If we have f of x and find its derivative of prime of x, then finding the derivative of f prime is called finding the second derivative. So second derivative just kind of means what you think. Do the derivative twice. Let's talk about some notations for that. So for the second derivative, the notation would be f double prime. Right, so you put two of those little apostrophes. And that just says, I took a derivative, and then I took it again. Right, that's called a second derivative. If you're using the Leibniz notation, it's also going to be d squared y dx squared. Right? And how you kind of want to interpret that is like you took a derivative, you got dy dx. Right, so this symbol here means take a derivative, and then you took a derivative again. So you get a d squared and a dx squared. But these are the two main notations that you'll be using. But whenever you see one of them, it means you're taking the second derivative. So basically here, we take the derivative of the derivative. There are several benefits to being able to find this function. And by the way, there are times when we can take the third derivative and the fourth derivative and the fifth derivative, and there are uses to those functions as well. In this class, we won't really go beyond the second derivative. There's not going to be much use for us beyond that. But there are disciplines that will require you to take even more derivatives. And those guys will have a lot of useful properties and can tell you a lot about the function that you're looking at. One use of the second derivative is in physics. So if we're looking at, for example, motion, is one way, is one area in which the second derivative is actually super important because it gives us acceleration. So let's say if we're given some function s of t, which is my position, at time t. So that's a function that gives me my position, or you can think of it as distance traveled or something like that. Then, if you take that a derivative, you end up with v of t, which is the velocity function. So if I give you a function and say, this gives you my position, how fast am I moving at a certain point? What you would do is you would take the derivative and you plug in that point and you find my velocity, and that's telling you how fast I'm moving. But you can take a derivative again. You can take the second derivative of the position, and that gives you the acceleration function. And so position, velocity, and acceleration are very important things to worry about when it comes to the physics of motion. There are many things that we interpret physically as acceleration. For example, the force of gravity is thought of as an acceleration, right? So the force of gravity is constant, but the idea is acceleration is how fast, and this is again going back to the interpretation of derivatives. If I take the derivative of a function, it tells me how fast that guy is moving. So you can think of velocity as how fast is my position changing, whereas in acceleration, you can think of that as how fast is my velocity changing. So if your speed is changing and you want to measure how fast your speed is changing, acceleration is how you do it. So if you think of the force of gravity, it's 9.81 meters per second squared. What that means is, if you drop an object and there's no air resistance or anything, the speed of that object will change every second. It will increase by 9.8. So that's actually a measure of how fast. So here's a measure of rate. And every time I see ROCs, I'm talking about rate of change. Rate of change of position. And this guy here is a measure of the rate of change of velocity. So this is one instance in which a second derivative is very useful. It's a physical application where you can talk about the rate of change of the motion of an object. And we will be doing problems like this where I'll give you a word problem and I'll describe how an object's position, and then I'll ask you to talk about its speed and its acceleration and all that stuff. But we'll do that a little more. I just want to introduce this idea to you. There's another idea of why a second derivative is important, and it's called concavity. So I'm going to give you a couple definitions, and then I'm going to show you how the second derivative is going to help us with this definition. So f of x is just some generic function. We say f of x is concave up. So that's the phrase I'm going to be using. That's the phrase I'm defining here. On some interval, if its graph always lies above its tangent line in that interval. What does that look graphically like? Well, that means you would have a function that looks like this. It has this particular kind of curve. Notice that if at any point I draw a tangent line, the function is always on top of the tangent line. Right? And so what that means, it's me describing how the shape of a function is. It's kind of shaped like a smiley face. You can actually remember a mnemonic here. concave up like a cup, right? Up like a cup. So whenever a function is concave up, it's you saying that it's shaped like a cup. Okay? Now, what would you notice about the tangent lines here? Notice that how would you describe what's happening to the slope of the tangent line? Right? Let's say this one here is like, I'm giving it a random number, like a half. What would you expect this one to be? Yeah? Something bigger, right? Something 2. In other words, notice here, in order to get this shape, what is happening is that the slope of your tangent line is increasing. And how do you measure something that's increasing? Well, you take a derivative. So that's going to be very useful. I'm going to be saying that all the time, eventually. So note, the slope of the tangent line is increasing in this case. We solved for, this is an idea I've introduced to you before, that increasing means slope is positive. Right? This means that if you're concave up, the slope of the slope is positive. In other words, this is me saying that the second derivative of my function will be positive. Because now I'm not looking at the function itself, I'm looking at the slope of my tangent line itself as a function. I'm looking at the derivative. I notice that that function is increasing, which means its slope must be positive. But the slope of the slope is just a second derivative. It's a derivative of the derivative. And so whenever that's positive, we end up with this sort of behavior in our function. And I'm going to talk about why this behavior is important. If you see this sort of behavior on a graph, it can mean a lot of things. You can interpret that in a lot of ways. It can mean, so I'm going to tell you what it means now, and then I'll describe concave down. So what this means. There are 3 main cases. So you can see something like, if you see, let's say something like this. Now one thing that will point out to you is that this guy here is going to be a minimum point. So one way to find the minimum of something is to identify a part of a curve that is concave up in this way, and I'm really after that point right here. So that's one thing you can notice from looking at concave up curves. Another thing you can notice is that what if it's not just like a cup where you can imagine that water can be held in it? What if it's going like this? Right? Kind of like how the graph of e to the x looks. What that would mean is that the function is increasing. And it is increasing faster and faster. Meaning that the rate of increasing is itself increasing. Right? So whenever you're using a function to measure something, it looks like this. Let's say, I don't know, you're running a store, you're measuring the number of sales per week. And you end up plotting that number of sales per week and end up with a graph like this. Now what that is telling you is that business is extremely good because sales are increasing and they're increasing more and more every week. So let's say this week I sold 10 products, the following week I sold 20, that was an increase of 10 products. But then the following week I sold 30, based on the following week I sold like 50. So from the previous week, that's actually an increase of 30 products, right? So it means like every week, sales are increasing, but they're increasing by more than what they increased the previous week. And if you have a situation like that, that is what your graph is going to look like. So if you're ever plotting something, some sort of function, and you see that behavior, what that tells you is whatever you're measuring is increasing, and it's increasing faster and faster and faster, right? If something was increasing by the same amount, it would be a straight line. It wouldn't look like a smiley face, right? But if something is increasing, and the amount it's increasing by is increasing, that's what you're going to see. You're going to see a concave up behavior. Conversely, if the thing is actually moving down, a third behavior you might see is if something is moving down like that, kind of like the graph of e to the minus x, then what this says is the function is decreasing. But it's decreasing slower and slower. So if that's your sales curve, then life is bad, but it's getting better, right? Yeah, sales are down, but it's kind of on the way up. You can kind of imagine maybe it might continue to do that and eventually increase. There's hope. You know, so you can kind of interpret things like that. So, and I'll talk about inflection, and I'll continue with that sales example and kind of talk about a situation. So there are three different kinds of behaviors that you might put together with a concave up curve. So concave up means up like a cup, means it's shaped like a smiley face, but it has certain interpretations that you can put on it. You can use it to help you find minimum points. You can use it to help you find when a function is increasing and it's doing so in an increasing fashion, or you can figure out when a function is decreasing and it's doing so at a slower fashion. It's actually decreasing by less than this. There's, of course, the opposite of concave up. There's concave down. And it's pretty much going to be everything I just wrote kind of flipped upside down. So let's just kind of go through this quickly. So not above its tangent line. So if it lies below its tangent line, it's concave down in a region or on an interval. If it's always below its tangent line in the region. So you end up with a curve that looks like this. At any given point where if you draw a tangent line, the tangent line will be above it. And the curve is actually below the tangent line. So that leads you to this mnemonic. Concave down like a frown. Concave down like a frown. So concave up like a cup, concave down like a frown. It's very important that you remember it. Think of it in that way. When you talk about concavity, think of it in terms of shape. You don't want to think of it in terms of increasing or decreasing, because you can be, your concavity has nothing to do whether you're increasing or decreasing. Here I have something that's concave up and it's increasing. Here I have something that's concave up but it's decreasing. So it doesn't have to do with going up or down. It has to do with the shape that you are while you're going up and down, and the interpretation that you can put on that. And by a similar argument, this kind of means your second derivative of all the points in this interval will be negative. So concave down like a frown. You're feeling down. You're negative. You're negative Nancy, right? This all goes with the little package that you're going to want to use to remember things. So concave up like a cup. Up, you're smiling. You're happy. You're positive. Your second derivative is positive. And what this means, well, again, I'm literally going to turn everything upside down. So if you see something like this, here's concave down and it's sort of level like that, that will give you a max point. right? So sort of like a parabola where the vertex is on the top. But the theory I'm giving you here doesn't just apply to parabolas, it will apply to any function. So parabolas are nice, you can find the maximums and minimums by using the vertex, like you had to do on the test. So you always know it's going to be minus b over 2a to figure out that point. But for general functions, there is no formula. And what we're going to be using is this guy to figure out max and mins for general functions. You can also use the first one. So if you see something like that, that will identify your maximum point. You can also see something like this, right? So this means the function is increasing. But it is doing so slower and slower. So to go back to that sales example, if you're plotting your sales during a certain period, and your graph is increasing but it's concave down, basically how you can interpret that is, yeah, life is good, sales are increasing, but I kind of realize that they're increasing by less and less. So my product is popular, but it's actually becoming less popular over time. And that can kind of hint to you, well, what might cause that? You know, when's going to be the tipping point where we're going to start losing money on this product? When is, you know, you can start to, when you start to follow the function, you're saying, I'm kind of seeing a pattern here, like something's going to happen in the future, right? So that's kind of why we need these functions, to sort of make predictions. You're plotting it here, it looks like this. You know, you don't want to be happy that, oh, sales are going up. Now it's kind of, yeah, sales are going up, but, you know, sales increased by 10 products the previous week, but it only increased by 5 products this week. So we're still in the green, but there's probably something on the horizon that we have to look out for, right? You can also have that third situation where it's moving down concave up. So we're shaped like a frown, but we're going down. So this means we're decreasing. But doing so more rapidly. Now in terms of sales, this would be very bad. This means you're losing sales and you're losing more and more sales every week. Right? That is a very bad situation if we go with that sales example. Okay. But again, if the functions we were drawing, for example, represented the number of deaths from a certain disease in a certain region, this might be good. The number of survivors, this might be good. But if you're looking at sales, this might be bad. So there's an interpretation that has to go along with what the function you're using represents. But the shape of your function can tell you a lot of things, and we can use that as an interpretation for, well, it would be based on whatever the function is measuring. But this kind of helps you to analyze a function on a deeper level. It's not just, oh, it's going up or it's going down. How is it going up? How is it going down? What does that tell you about the future? What does that tell you about what's on the horizon? What does that tell you about what we need to change, if we need to change, if we need to do more of what we're currently doing, if we need to do less of what we're currently doing? See, those kind of things you can tell by using the second derivative. I want to tell you about inflection points. So there's a lot of concepts here, and we'll talk a little bit more about concepts next class as well. So here's a definition. We can talk about an inflection point. An inflection point. So I'm just telling you what these things mean, but I'll tell you specifically how to locate them in the next class. An inflection point of f is a point where what happens at an inflection point? Does anyone remember? Yep?
That's when the concavity changes.
When the concavity changes. When we change concavity. Meaning, before that point, we were concave up, and then we suddenly switched to concave down. Or vice versa. Before that point, we were concave down, and then we suddenly switched to concave up. So that would look something like this. That point here is called an inflection. Notice on this side, here we're concave down like a frown, and a smile, and a sad face. But over here, I'm concave up like a cup. The point where I actually made that switch is called an inflection point. So, to go with our sales example, that point would be very good, right? Whatever we did at that point in time for our business was the right decision. Things were great before, but something was kind of happening, and then boom, something happened. What did we do on that week? We need to do more of that. You know what I'm saying? So that can kind of hint to you certain things. Or it could be vice versa. It could be like this, and then that happens. So yeah, things were good, but they're still kind of good, but they're kind of getting worse at the same time. Right? So you can have inflection points like that. You can also have them going down. So you can have something like this. That would be an inflection point. And something like this. And that would be an inflection point. So those points would kind of identify to you when your function changed its behavior. From doing whatever it's doing faster and faster, slower and slower, to the opposite. So those points are going to be important. And I'll talk about how to identify these points in the next class. We'll stop there. We didn't finish, so no homework for next.